How's it going, everyone? This is going to be a walkthrough of a typical confidence interval question. So we have the temperature of a piece of machinery during operation is measured 20 times. And over those 20 times, we have an average temperature of 75 degrees and a standard deviation of 8.2 degrees. So we're asked a few questions here. The confidence interval question setup can be different, but typically you'll have a sample size, in our case 20, an average value, and a standard deviation when we are asked to calculate a confidence interval. And here we're asked to calculate a 90% confidence interval. So the confidence interval is equal to the sample mean, represented by x bar here, plus or minus the margin of error. And that margin of error is the critical t-value multiplied by the standard deviation and divided by the square root of sample size. Because we have a sample standard deviation, we are using a critical t-value. And that t-value is the only value in this equation that we are not given. So to find that, if we draw our distribution, that central part is 0.90 because we're looking for a 90% confidence interval, 0.90 in decimal form. And because of symmetry and because the area under the entire curve has to be equal to 1, each tail is going to be size 0.05 or 5%. So that's our tail size. The other piece of information we need to find a t-value is the degrees of freedom, and that's equal to sample size minus 1. Now our sample size is 20, so our degrees of freedom is going to be 19. So we go to the t-table, we look for 19 degrees of freedom, and a tail size of 0.05. So there's our t-table. The top row is where you select your tail size, and the leftmost column is where you select the degrees of freedom. So the tail size we're looking for is 0.05, which is right here. And we want to match that up with 19 degrees of freedom. So we know what column we're in, then we look for 19 degrees of freedom. That tells us what row we have to be in. And that gives us our critical t-value, which is 1.729. 1.729. So this is going to be a positive 1.729, and this is going to be a negative 1.729 on the t-axis. The t-table just gives us the positive value, and it's up to us to know where is it negative and where is it positive, 1.729. So now we have everything to perform the calculation. X bar plus or minus TS over the square root of n. Our X bar is 75 degrees. Our t-value, 1.729. Our standard deviation was 8.2 degrees. And our sample size was 20. So we'll have the square root of 20 at the bottom. And then we just perform this calculation. So 1.729 times 8.2 divided by the square root of 20 is going to give us 3.17 approximately. 3.17. So 75 minus 3.17 is going to give us 71.83. And 75 plus 3.17 is going to give us 78.17. And that is our 90% confidence interval. That is our answer to part A. Now, part B says if the population standard deviation is assumed to be 8, how many measurements are needed so that the margin of error for a 95% confidence interval does not exceed 2 degrees? Okay, so here we're being told the margin of error. It has to be 2 degrees or less. And we're being asked, how many measurements do we need? What should the sample size be? So we've already discussed how the margin of error, now here we have a population standard deviation, so instead of TS over root n, it's Z sigma over root n. Sigma because it's the population standard deviation, and Z because we're using a critical Z value instead of a critical T value. If we rearrange this equation to solve for n, what we get is that n equals Z sigma over the margin of error squared. Now, in this equation, the only thing we're not given is Z. We're told the population standard deviation is assumed to be 8 degrees. We're told the margin of error must not exceed 2 degrees. So we just need to find the Z value, knowing that we're looking for a 95% confidence interval. So because we're looking for a critical Z value, we don't need to know the degrees of freedom. If we draw our distribution here, and our middle is 0.95, which is 95% in decimal form, because we're looking for a 95% confidence interval here, each tail is going to be size 0.025. 0.025, because the total area under the curve has to add up to 1. So if we go to the Z table, we look for a probability of 0.025, or whatever is closest to it, we will get our corresponding critical Z value. So we go to that standard normal distribution table here. We look for whatever's closest to 0.025, and we actually find something that is precisely equal to it, right here, 0.025. And again, if the exact value you're looking for isn't there, just take the closest value, and if two values are equally close, then find the corresponding Z value to both of them and take the average of those two. So in our case, we have one value here that's closest, in fact exactly equal to it. The corresponding Z value, you'll have it up to one decimal place in the leftmost column, which is 1.9 or negative 1.9. And the second decimal place will be in the top row, which is 6. So our corresponding critical Z value is negative 1.96. Now that's the negative value. It's up to us to know that it's here, negative 1.96. To the left of center, and to the right of center, the value is 1.96. Another way you can find the critical Z value is actually using the T table, but infinitely many degrees of freedom. So on the T table, there's our tail size of 0.025. And if we match that up with infinitely many degrees of freedom, there's infinity right here, what we get is 1.96. And as always, the T table gives us the positive value. So now we have everything we need to find the sample size. So n equals Z sigma over E squared. Same formula right here. We have our Z value, 1.96. We have our population standard deviation, which is assumed to be 8, based on the description right here in the question. And we have our margin of error, 2 degrees. So we have a 2 on the bottom here, and then we need to square all of that. So 1.96 times 8 divided by 2 is 7.84. And 7.84 squared is approximately 61.47. Now, since we're looking for sample size, we can't really have an answer that's not a whole number. We're talking about the number of measurements done. Or in a different type of question, might be the number of people surveyed. It has to be a whole number. Now, if you look at this equation here, E, our margin of error, cannot exceed 2. So it'll be 2 or less. And if E becomes smaller, well then this entire expression will become bigger because you're dividing by a smaller number. Okay? So if 2 is the maximum value for your margin of error, well then what we get for n is the minimum value. Our sample size has to be at least 61.47. So if we're going to turn that into a whole number, we have to round it up to 62. Even though 61.47 would typically round to 61, we need at least 61.47 measurements, which means 61 is not enough. So we always round up, and that gives us an answer of 62, and that's our answer to part B. We need at least 62 measurements so that our margin of error does not exceed 2. And that's how you do those kinds of questions. So I hope that helps, and until next time.